So I just overheard Ari make a point to one of your teams. And sorry, I didn't mean to interrupt. But I just overheard her make a point that I want to amplify. We cover in this course two distinct methods for solving systems of linear equations. One of them is called the substitution method. The other one is called the elimination method. What you should have noticed if you used both of these methods on this sheet is that all roads lead to Rome, right? You should end up with the same solution for this system regardless of which method you use. If it were not so, we wouldn't learn both methods because at least one of them would be wrong. Right? The good news is that because both of these methods work every time, you are completely free, unless a question asks you otherwise, you are completely free to choose whichever method you will remember better, whichever method you find works better, whichever one you find easier to remember, whichever one tends to lead you through a process that involves less hairy numbers. Whichever one you connect better with, you can use, unless a question asks you otherwise. And this is probably the only time this semester when I will ask you specifically to use one method or the other. So I am interested in you gaining practice with both methods, but really when the rubber meets the road, whichever one works best for you is the one that you should take away from this semester. That being said, let's look at both. So starting with this system of equations, if I ask you to use the substitution method, what are you going to do? What's your first move in trying to use the substitution method to solve the system, Brian? Isolate the x. So you chose the x. Why? Okay. Yeah. How could you tell that it's? I happen to agree. I think. But what is it that leads your eye to the x as being something simple to isolate?
Well, it's right there.
It's right there. Yeah, exactly. It's the first thing that your eyes meet when you look at this system of equations is that x in the upper left. And because it's by itself, right, it doesn't have a coefficient except 1 in front of it, it would seem to be a pretty easy target. So that's where my mind would go if I wanted to isolate one of the variables. We could equivalently choose the y in the second equation to isolate. It doesn't matter. There are a lot of choices that we make along the way here that are really just matters of taste more than they are matters of correctness. But I'm going to follow Brian's suggestion and focus on this x and say, let's isolate that x. Well, what does isolating mean? What does that look like? What's the process? Yeah. So this is the reason that in Module 2, we learn how to solve an equation for one variable in terms of another. This is one of the places, one of the many places where that skill shows up. In order to solve this equation for x in terms of y, we just need to move that other term, the 2y, from the left-hand side of the equation to the right, which we can do by subtracting 2y from both sides and getting x equals 5 minus 2y. So we've successfully rearranged the first equation to make x the subject, to get the x by itself. So that was our first step. But that doesn't explain the name of this method. We haven't done any substitution. What substitution do we actually do? What do we substitute and into where?
The 3x. So what you have to do is you do 3 parentheses 5 minus 2y parentheses plus 1.
Yeah. Exactly. So the first equation is telling us that regardless of what a relationship exists between x and y, as soon as we know what y is, we can find out what x is by subtracting twice y from the number 5. So anywhere that x shows up in this system, we can replace it with 5 minus 2y without changing the solution of the eventual system. So, in particular, in our second equation, we can replace that x with, and Brian makes a good point, use parentheses anytime you're substituting in an equation so that you don't leave something out. But we can replace x with 5 minus 2y. And the net result is that we now have an equation, 3 times the quantity 5 minus 2y plus y is equal to negative 5. This equation has only y's in it. It no longer has multiple variables. We only have a single variable now. And it happens to be a linear equation, no exponents, because that's a later in the course, right? That's a tomorrow thing. It's not a today thing. So we have an equation that we can solve to find out what the value that y should take is. So that, I think, is the hard step. is that substitution step, just rearranging the first equation or the second equation and plugging the results of that rearrangement into the other equation to eliminate a variable. That is the priority. So how are we going to solve this equation? This is back in Module 2 turf now. How can I solve 3 times the quantity 5 minus 2y plus y equals negative 5? Yeah, first let's simplify the left-hand side by getting rid of those parentheses, distributing multiplication across addition. So 3 times 5 is going to give me 15. Whoops. 3 times negative 2y minus 6y. And then I'll still have plus y equals negative 5. Okay. What's negative 6y plus y if I combine like terms? Negative 5y. So I'll have 15 minus 5y equals negative 5. What's my next step? Yeah, we're using order of operations backwards. Subtract to move the 15 to the other side. That leaves me with negative 5y on the left. And on the right, negative 5 minus 15, negative 20. Ample places to make sign errors here, so be careful in your signed number arithmetic. And what's my last step to get the y by itself? Divide by negative 5 on the left and on the right. What's negative 20 divided by negative 5? Positive 4. Great. So now we know what numerical value y should take. Y should be equal to 4. But of course we can't stop here. What still do we not know? We don't know x. We can't stop in a solution of a system of equations until we know the values that all of its variables need to take. The advantage is, now that we know one of the values, we can use that value to find the other. How do I use the fact that we know y is equal to 4 to find a value for x? Yeah, and I heard Ari making this great point earlier as well. We can plug this y equals 4 into where? We could plug it into the top equation. We could also plug it into the second equation. We could also plug it into our rearrangement equation, x equals 5 minus 2y. We can plug it into any equation which we know to be a true reflection of the relationship between x and y, and we should get the same answer. If you're concerned about whether y equals 4 is correct, you might try plugging it in several different equations along the way, because you should, if it's a correct answer, get the same value for x each time that you plug it into those different equations. I'm actually going to make the choice, because I find it's going to be a little simpler, to plug this value into our rearranged equation x equals 5 minus 2y. The reason I like that, and the reason you might also like it, is that now finding x is going to require no algebra, but only arithmetic. Because the x is by itself already in this equation, all we have to do is simplify the arithmetic on the right-hand side. 5 minus 2 times 4. What's 5 minus 8? We end up with negative 3. And therefore, we've found our value for x. So this problem illustrates kind of the basic contours of using the substitution method. Substitution is a really natural thing to do if one of your original equations already has the variable isolated. So, for example, I think there are some examples in your workbook and on Alex and places like that where actually the problem that you get from the outset already has something like x equals 5 minus 2y. It's already kind of set up for you. In a situation like that, you don't even have to do the work of isolating one of the variables. You can skip straight to the substitution. Plug 5 minus 2y in for x in the second part of the equation. So even though both methods that we're talking about today will always work, there are some scenarios in which you might, choosing to use substitution might give you a quicker process than choosing to use elimination. And in particular, if one of the equations is already solved for one of the variables, substitution is a natural choice in such a case. That wasn't the case here, though. Here we started with both equations having both variables on the same side. So here, we had to do the additional step. of isolating a variable.